Okay, so let's finish this problem. So we're supposed to find resistor R4, and since we have introduced Kirchhoff's voltage law, somewhere in this analysis and this solution we're going to use Kirchhoff's voltage law. So as I said, we are given the source voltage, we are given the source current, we have resistor R1 and R2 and R3 identified. So in this problem, we will use both Ohm's law and Kirchhoff's voltage law. So let's first use Ohm's law to find the voltage drops across each of the known resistors. So 1, 2, and 3, we are going to apply the fact that 10 milliamps is the source current through every one of these resistors, even R4. So we find voltage drop V1 is 1 volt. Voltage drop V2, 4.7 volts. Voltage drop V3, 10 volts. And in each case, we use the product relationship I times R of Ohm's law to solve. So now we can switch to Kirchhoff's voltage law to find the voltage drop across R4 and allow us to go back to find the voltage using the voltage drop to determine the resistor value. So let's use the relationship that the net sum is equal to 0. So the source minus V1 minus V2 minus V3 minus V4 is equal to 0. So when we do that, we have known values for everything but the voltage drop across V4. So when we put our values in here, 51, 4.7, and 10 volts, we get 34.3 volts. Minus V4 is equal to 0. Use your algebra. V4 is equal to 34.3 volts. So now I can switch back to Ohm's law. Ohm's law now says that we know V4. Let's calculate for R4. So R4 is equal to V4 over the total current. 34.3 volts dropped. 10 milliamps. 3.43 k ohms becomes the value of R4. So R4 is most likely a 3.3 k ohm resistor. Why? Because that is a common value that you could find in the benchtop. Because 3.43 is within a standard tolerance range of plus or minus 5%. So now you see why we use those tolerance ranges of 3.3 k ohms. So it's a good idea to get used to calculating those percentages and determine, okay, can I find a standard produced resistor to put in this circuit or to identify that resistor accordingly. So Kirchhoff's voltage law then is another way, we need to look at another way to state the voltage law. So far we've seen how Kirchhoff's voltage law can be applied to a series circuit with a voltage source, but it can also be applied to other types of circuits. So we go back to our relationship where we're saying that the sum of all the voltage drops equals 0. If a voltage source that is present, it is simply treated as one of the terms, okay? So in applying equation 5.4, an algebraic sign then is given to each voltage in the path depending on whether it's a voltage rise or a voltage drop. Just depends on which way the source is placed in the circuit. A voltage across a resistor can appear as either a rise or a drop depending on the path direction chosen, your positive or your negativeness of the polarity in the circuit. So you'll need to assign algebraic signs to voltage rises and voltage drops in a consistent manner. A practical example of using Kirchhoff's voltage law around a loop with no source is given in the application activity in Chapter 6. So we're looking ahead there. Sometimes you will see an equation such as 5.4 expressed in shorthand notation using the Greek letter sigma to denote the summation. So if we capture what we've written up here as a shortcut relationship, the sigma says we're going to sum all of the values starting at I equal 1 to the nth value for Vi. Okay, so V sub I and that little I equal 1 is the same I. So we would start with I equal to 1 and go to the nth value. If it was 5, that n would be replaced with a 5. Okay, let's take a look at another example here. Determine the unknown voltage drop V3. Okay, so we've got V3 down here on resistor R3. In this case, we've got two sources, but you should notice immediately the sources are pointing in opposite directions. So they are, one is a rise, one is a drop. So we look at the fact that we're going to have a reduction in this circuit of 15 volts in our source voltage. So by Kirchhoff's voltage law, the algebraic sum of all the voltages around the circuit is 0. Okay, that's by definition. The value of each voltage drop except V3 is known. Substitute the values into the equation. So we use the stated relationship. We sum, let it equal to 0, and then start dropping the values in. 50 minus 15 minus V3 minus 6 minus 12. And so when we sum out these together algebraically, we will end up with 17 volts left over. Minus V3 equals 0. Minus V3 is equal to minus 17. All we did was move the 17 volts to the other side of the equation. The minus signs cancel, and we have V3 equal to 17 volts. The voltage drop then across R3 is 17 volts, okay, and its polarity is as shown. Okay, so Kirchhoff's voltage law. So now we're going to move on to a value of circuits here. We're going to move to a configuration value, something known as voltage dividers. Voltage dividers are very prevalent in things like power supplies and places where we want to pick off a voltage value from a consistent source. So when we come back, we're going to define what a voltage divider is and see how we can use them in a circuit to deliver multiple potentials in a circuit using one source.